Hey guys, so welcome back to another lecture video. In this video, we are going to learn how to perform calculations involving pH, pOH, the concentration of hydrogen ion, and the concentration of hydroxide ion. Now, before we move forward, I do want to mention that hydrogen ion can also be equally expressed as a hydronium ion. And so I believe I discussed that in previous lecture videos. So let's go ahead and start. From previous lecture videos, I went ahead and introduced the definition of pH and pOH. And so the pH is equal to the negative log of the concentration of hydrogen ion and the negative log of the concentration of hydroxide ion for pOH. And so if we wanted to use these equations, reading from left to right, this is basically telling us is that if we want to find the pH, we're going to take the negative log of the concentration of hydrogen ion. So it's implying that this value is somehow provided to us one way or another. And if we wanted to find the pOH, we would have to take the negative log of the concentration of the hydroxide. And so once again, it's implying that this value is already given to us, or will be given to us one form or another. And so before I move forward, I keep on mentioning the concentration of. And so if you guys recall from the previous chapter, concentration just represents the amount of substance per given unit of mass or per given unit of volume. However, in this case, the unit of concentration that we're referring to is going to be molarity. And molarity is a ratio of the number of moles of solute over the volume of the solution, which is 1 liter. So 1 liter of solution. And so any brackets that you guys see when we perform these calculations basically represents the molarity of whatever substance it is that's inside the bracket. So the substance can either be hydrogen ion, it can be a hydronium ion, or a hydroxide ion. Okay. All right. And so these two equations allow us to determine the value for the pH if we are given the hydrogen ion or the hydroxide ion, the concentration of those two substances. And so what if we flip the scenario? What if we're given pH or pOH and we want to find the concentration of hydrogen ion? And so what we're going to do is we're going to rearrange this equation so that we're simply solving for the concentration. Now, I'm just going to go ahead and do it with respect to pH, but this derivation also applies to pOH. So I'm going to go ahead and take this equation, pH is equal to the negative log of the concentration of hydrogen ion. And I'm going to go ahead and solve for the concentration of hydrogen ion, since that's what I want to find. And so to do that, I need to bring the negative to the opposite side. So I'm going to divide by -1, making it a negative pH. And that's going to equal to the log of the concentration of H+. And so to get rid of this log, we're going to have to perform the antilog. And on your calculator, you should type in second and then log to bring up that function. And so if I simplify my work, I basically get the negative, 10 to the negative pH is equal to the concentration of hydrogen ion. And so this is telling me, and I'm just going to go ahead and I'm going to move this actually to the side. Okay. All right, I'm just going to move this to the side just because I wanted to get all of the equations in one slide. And so the result of this derivation produces this equation, where the concentration of the hydrogen ion is equal to base 10 or 10 to the negative pH. Okay. And so I'm just going to go ahead and simply rewrite that. So the concentration of H plus is equal to base 10 the negative pH. And so this the location where the pH is like an exponent. So it's 10 to the negative whatever power. All right. And so we're going to go ahead and use this equation if we want to find the concentration of hydrogen ion if we're given the pH. And so I'm going to go ahead and mimic this same formula for pOH. And the derivation is going to be the same. You guys can go ahead and do it on your own. But the result of me basically solving for the basically the derivation for me solving for the concentration of hydroxide is very similar to what I just did here. The only thing that's different is we're just changing the substance from hydrogen ion to hydroxide ion. And so the final equation that I'm going to get is the concentration of hydroxide is equal to base 10 and then to the negative pOH. Okay. And so I'm going to go ahead and use this form if I want to find the concentration of hydroxide ion. And we're given the pOH. Okay. And so I'm just going to go ahead and box all four of these equations. And so you should have these equations in your reference page or on your notes. Now, these two equations only allow us to convert from pH to the concentration of hydrogen ion and vice versa. And these two equations only allow us to convert from pOH to the concentration of hydroxide ion and vice versa. But what if we're given the pH, and what if I want to figure out the concentration of hydroxide ion? Notice that I can't use the four equations to make to bridge one substance to another. Okay? And so for me to kind of go across, for me to transform pH into, for example, concentration of hydroxide, I need a couple more equations to make that relationship. And so the first equation is going to be the pH plus the pOH is equal to 14. And when you guys do the acid-base lab, you guys should be able to see how pH is related to pOH. And so if pH decreases, then pOH increases, such that the sum of the pH and the pOH is equal to 14. at 25 degrees Celsius. Okay. And so if the temperature is not at 25 degrees Celsius, this number is going to be slightly different. But we're not going to be concerned about that for this class. We're just going to assume that everything is at 25 degrees Celsius. So therefore, we can use this value 14. Now, this equation only allows us to go from pH to pOH, or vice versa. The second equation allows us to make a relationship between the concentration of hydrogen ion and the concentration of hydroxide ion. And that's simply going to be the product of the two. So the concentration of H plus times this by the concentration of OH minus is equal to 1.00 times 10 to the negative 14. And once again, this value holds true when the temperature is at 25 degrees Celsius. And so overall we have overall we have 6 equations that allow us to go between pH, pOH, concentration of hydrogen ion, concentration of hydroxide ion. Great. And so what we're going to do is we're going to look at a couple of examples to demonstrate how these equations are used to convert from one substance to another, from pH to pOH, etc. All right. So the first example that we're going to do is this one. So if the problem had mentioned that the concentration of hydrogen ion or the concentration of a hydronium ion is equal to 2.891 times 10 to the negative 3 molar, this question is going to ask us to determine the pH, the pOH, and the concentration of hydroxide ion. And so what we're going to do is we're going to look at our given value and see what it's relating to. So in this case, it's talking about the concentration of hydrogen ion. And we're going to first see which of these 3 I can solve for. Okay. And so if I scroll through my equations, I was given the concentration of hydrogen ion. And so I see the hydrogen ion. I'm going to shift to a different color. Let's do pink. I see hydrogen ion in 2 places, here and here. Okay. Now, notice that if I look on the left-hand side of the equation that's presented at the top left corner, notice that I can easily solve for the pH since the concentration of hydrogen ion was given. Okay. And so if you look at the bottom equation, notice that there's no pH over here. Technically, I can solve for the concentration of hydroxide, but we'll just do that at a later time. And so since the concentration of hydrogen ion was already given to me, I'm going to go ahead and solve for the pH first. And so the pH is defined as the negative log of the concentration of H+. And since this value is already given to me, I'm just going to go ahead and plug it into this equation, so that I get the pH is equal to the negative log of the concentration of 2.891 times 10 to the negative 3. Okay. And so when you guys are plugging just this part in your calculator to solve for the pH, so plug into calculator. It really depends on the type of calculator that you guys have. I have a Casio, and with my Casio, I can just plug everything as I see it from left to right. For some TI models, I think it's the base model of the TI, you might have to put in that negative sign after you type in the number. I don't know, there's just some weird ways to input these values into your calculator. And so for me, I'm just going to go ahead and type in negative, then log, then this value. And then I'm going to hit the equal sign. And so when I hit the equal sign, I get a very large number. Or I'm sorry, not a large number. I just get a whole bunch of numbers. So I get 2.538 95191. And so this is the raw calculator answer that I get. And so I want to report the correct number of significant figures or significant digits. And so this is something that's very intrinsic to log functions. Notice that, I'll go ahead and highlight it, these four values, so these four digits, they're all significant digits. So there's four significant figures or significant digits before I plugged in that value to determine my pH. And so I want to retain that same number of significant figures. However, since my function is not a multiplication, division, addition, subtraction, my function is a log, the rules for sig figs changes. And so if I have four significant figures, when I take the pH of that value, the four significant figures is going to be represented by four places after the decimal. So 4 decimal places. Okay, so did you guys get that? So 4 sig figs, 4 places after the decimal. And that's going from concentration or molarity into pH or pOH. Okay. Now, if I would just want to report 4 decimal places, I'm going to go ahead and take this 5 and then round this guy up, and that will also round that 8 up just because it's a 9. And so the pH is going to be 2.5390. So once again, notice how I have 4 decimal places. And so this is going to be the pH of my solution. Okay, so I'm going to go ahead and write that over here. So I've now solved for the pH, and that's 2.5390. Awesome. And so the next item that we want to solve for, I'm just going down the list here, is pOH. And so pOH is going to, now if you guys notice, I currently have pH and I want to solve for pOH. So if I scroll up, notice that there's a relationship between both of those pH scales. If I add up both of those numbers, they equal to 14. So I'm going to be using this equation to solve for my pOH. So let's go ahead and do that. So since pH plus pOH is equal to 14, I'm going to take this value and I'm going to go ahead and plug it in to pH. So that's going to give me 2.5390 plus pOH is equal to 14. And so to solve for pOH, I'm going to subtract by that same value on both sides of the equal sign. And so the pOH is going to equal to 11.4610. And so since there are 4 decimal places when we plugged in the pH, there also needs to be 4 decimal places to represent the pOH. Okay. And so how come this 11 doesn't count? How come the first 2 digits does not count in terms of significant figures? And so this is coming from the log function. So whenever you take the log, I don't know, like 1.00 times 10 to the negative 4, what happens is that this 4 is brought, this 4 from the exponent is brought kind of forward, if you will. And so it's going to be 4, and then, log of 1, right? And so this log of 1, and so what you get is just this 4. And so basically the exponent becomes the first digit. And because this first digit is coming from the exponent, and since the exponent is not part of our significant figure count, right? So when we look at this, when we calculate the number of sig figs, this is 3 sig figs. Therefore, we ignore the exponent that was brought in front of the number. Okay. And so we're going to go ahead and ignore this. And this is going to represent 4 decimal places, which equals to 4 significant figures. Okay. All right, so after we solve for the pOH, we're just going to go ahead and write that down. So that's 11.4610. So the last item that we're going to solve for is the concentration of hydroxide. And so to solve for the concentration of hydroxide, there's a couple ways that you guys can do this. Either path will get you to the right answer. And so you guys can, I'm going to erase some stuff here. And so since the concentration of hydrogen ion was already given to you from the very beginning, you guys can go ahead and use this equation to solve, let me erase that, to solve for the concentration of hydroxide. Another way that you guys can solve for the concentration of hydroxide is using this equation. Okay? And so it doesn't matter which one you guys choose, just as long as you're solving for the concentration of hydroxide ion and you're plugging in the correct number. Okay? And so if we're going to be using this equation, we need to make sure that we're plugging in the pOH. If we're using this equation, we need to make sure that we're plugging in the concentration of hydrogen ion. And so I'm going to go ahead and just use this equation at the top. And so since the concentration of the hydroxide ion is equal to base 10 of negative pOH, since my pOH is 11.4610, I'm going to go ahead and plug that guy into here. So therefore, the concentration of hydroxide is equal to 10 base 10 negative 11.4610. Now notice that I'm going from pOH back to concentration. And so, oh, actually, I'm going to take a step back here. So, the pH and pOH, they are unitless. Okay. So for those who don't like writing your units at the very end of a number, you guys will absolutely love calculating pH, because all you have to do is spew out the correct number of significant figures and you're done. So since we're going from pOH back to concentration, I need to make sure that I'm representing the unit for concentration, which is molarity. Okay. And so I'm going to plug this into my calculator, because that's what the concentration of hydroxide is equal to. And so when I'm typing this into my calculator, I'm going to find that second button. And then I'm going to follow it up by pressing log in my calculator. And that should bring up my base 10. Okay. And so I'm going to go ahead and plug in negative 11.4610. A lot of students forget this negative sign. And if you forget that negative sign, you're going to get a very odd looking number. And so let's go ahead and plug that into the calculator. And therefore, the concentration of the hydroxide is equal to 3.459 times 10 to the negative 12 molar. Okay? So you need to make sure that you add the unit of molarity, since now you're talking about the concentration of hydroxide. And once again, let's talk about significant figures. Did I report the correct number of sig figs for my concentration of hydroxide? And so since this value is this negative 11, remember that we have, so this negative 11.4610, we have 4 decimal places. And so our answer, our final answer, must represent 4 sig figs. Okay. And so when you're going back to concentration, it's as if life is normal, right? You don't care if those digits are after the decimal or before a decimal. It's literally the first 4 digits that you see. Make sure that you're rounding it correctly. Life is only complicated when we're taking the negative log of a specific value. And so when we take the negative log of a specific value, then we have to keep in mind the number of decimal places that's being reported. Okay. So I'm just going to go ahead and write that in. So 3.459 times 10 to the negative 12 molar. Okay. All right, so we have solved for pH, pOH, and concentration of hydroxide. Let's go ahead and take a step back and think about the concept with respect to all of these values. Like, what are all of these values telling us? And so if you compare, I'm going to do this in yellow, if you compare the concentration of hydrogen ion and the concentration of hydroxide ion, which value is larger? I'm going to erase this, and I'm going to highlight this in yellow. So I'm going to look at this concentration, I'm going to look at this concentration. Which of these two values that I highlighted is going to be larger? And so if you had said the concentration of H plus, this guy, or this guy, then you're absolutely right. So negative 3 is closer to 0 than negative 12, making negative 3 larger than negative 12. So negative 12 is smaller. And so this is telling us that we have more hydrogen ions than hydroxide ions. And so since the concentration of H plus is greater than the concentration of OH minus, this is telling us that our solution is acidic. Now, what if we didn't see that? What if we didn't think about making those comparisons to determine if the solution is acidic or basic or neutral? Now, another way that you guys could have done it is simply by looking at the pH. This is something that you guys are used to seeing, especially if, for example, you own a pool or an aquarium. And so if you look at the value for pH, notice that it is 2.5390. And so if the pH is less than 7, that's telling us that the solution is acidic. Okay, and it makes sense. So these answers should coincide. If they're not aligning, then there's something wrong with your calculation or your derivation or something. And so if you guys recall from the previous lecture video, if the pOH is greater than 7, that's also informing us that the solution is acidic. So all three of these will tell us whether or not our solution is acidic or basic or neutral. And all three of these derivations, for lack of a better term, are all pointing toward one specific item, such that this solution is acidic. It doesn't matter which of these you guys use, it's telling us that the solution is acidic. Okay. All right, so let's go ahead and continue. We're going to go ahead and do one more example. So let's just say that our pOH was given to us, and the pOH is 5.32. The first thing that I'm going to solve for is the pH. And so to solve for the pH, I need to find a relationship that relates pH and pOH. And so if I scroll through my list of equations, I know it's kind of messy here, so I'm going to erase some stuff. Okay. Okay. And so since I'm trying to go from pH to pOH, from one pH scale to another pH scale, notice that I'm probably going to have to use this relationship or this equation. And so pH plus pOH is equal to 14. If I plug in the given value, in this case it's pOH, I'm going to go ahead and solve for pH. So I'm going to subtract pOH to the other side. And so pH is going to equal to 14 minus pOH. So if I plug in the value for pOH, that's going to be 5.32. So therefore pH is equal to 14 minus 5.32. So if I solve for pH, that value is going to be 8.68. Okay. And once again, notice that I started off with 2 places after the decimal. And so when I calculate my pH, I'm going to make sure I keep to 2 places after the decimal. Okay. All right. And so now that I've figured out that the pH is 8.68, I'm going to go ahead and determine the concentration of hydroxide ion. And so here in this case, I have two given values. I have 8.68, which equals to the pH, and I have 5.32, which equals to the pOH. It only makes sense for us to use this value since the substance that I'm looking for is hydroxide. So I'm looking for an equation that relates pOH to concentration of hydroxide. And so if I scroll up and if I look at my equations, let's do this in green this time. Notice that for me to convert from pOH to concentration of hydroxide, I'm going to use this equation that I highlighted in green. Okay. So let's see here. The concentration of hydroxide is equal to 10 to negative pOH. Okay. So it's very similar to what we did in the previous example. So all I'm going to do is plug in this 5.32 into the exponent. So the concentration of OH minus is equal to base 10 minus 5.32. Oops. And so this is what I'm going to plug into the calculator. Now, if you plug that into the calculator, the concentration of hydroxide is going to equal to 4.78630092 times 10 to the negative 6. And once again, since I'm solving for the concentration of hydroxide, I need to remind myself to add in the unit of molarity at the very end of my answer. All right, so let's talk about significant figures. In this scenario, we're going from pOH to a concentration. And so remember that if I have a p value, pH or pOH, I'm looking for the decimal place. And if I'm converting that into concentration, I'm just converting all those number of places after the decimal into the first X number of significant figures that I see. And so here I have two decimal places. And so since I have two decimal places, that translates into two significant figures. And so the first two sig figs that I'm going to look at is 4 and 7. And so that tells me that this next digit to the right of 7 will round that value up. And so the concentration of hydroxide is going to equal to 4.8 times 10 to the negative 6 molar. So once again, this is representing the two significant figures, which reflects the number of significant figures in that pOH. So it's two decimal places. Okay. So if you guys kind of keep this formula in mind, so you can even do it with pH as well. pH is dP, and the concentration of H plus is going to be significant figures. So you just need to kind of fill in the blank, right? So if you have 3 sig figs for the concentration, that means you have 3 places after the decimal that you need to report. Okay. Hopefully that makes sense. Okay. I'm going to erase this. All right, so we figured out that the concentration is going to be 4.8 times 10 to the negative 6 molar. And so now that we have the concentration of hydroxide, we can go ahead and solve for the concentration of hydrogen ion. And once again, you guys can do this one of two ways. You guys can solve for the concentration of hydrogen ion from this hydroxide, or you can solve it using pH. And so I'm going to go ahead and solve it using the hydroxide, just because I haven't used that formula at all in this video lecture. And I want to show you how it's utilized at least one time. And so since we have the concentration of hydroxide ion, we're going to be using the concentration of H plus times this by the concentration of OH minus equals to 1.00 times 10 to the negative 14. And I'm going to go ahead and plug this concentration in. And so when I do so, I get concentration of H plus times this by 4.8 times 10 to the negative 6 is equal to 1.00 times 10 to the negative 14. And so this value is also unitless. It's not molarity or anything like that. It's KW. It's a topic that is out of the scope for Chem 104. And so just know that it's unitless. And so all you guys are going to do is divide 4.8 times 10 to the negative 6 to the other side. And so the concentration of H plus is equal to 1.00 times 10 to the negative 14. Divide this by 4.8 times 10 to the negative 6. And so if I divide, the concentration of H plus is going to equal to 2.08929,613 times 10 to the negative 9 molar. Okay. Once again, the brackets are present, therefore the molarity unit must be present. Let's go ahead and talk about sig figs. So if you are looking at the operation that we just performed, I see 2 sig figs here, and 2 sig figs is the least, and so therefore I'm going to report the first 2 significant figures that I see going from left to right. And this 8, we're going to go ahead and round it up so that our concentration is going to be 2.1 times 10 to the negative 9 molar. And so this is going to represent the concentration of hydrogen ion. So I'm going to go ahead and plug that in to my final answer here. So that's going to be 2.1 times 10 to the negative 9 molar. Very similar to what we kind of discussed in the previous example. What do all of these numbers tell us? What is it conveying to us as the reader? And once again, there's 3 ways to go about and interpret this data, so to speak. We can go ahead and compare the concentration of hydrogen ion and hydroxide ion. And so if you look, I'm going to do this in orange. If you look at the value, which of these 2 values is larger? Now, if you had said the concentration of OH is larger, then you're absolutely correct. So this negative 6 is closer to 0 compared to negative 9. And so negative 6 is going to be a larger value than times 10 to the negative 9. I'm not really paying attention to these numbers just because the power, this scientific notation, the times 10 to the negative 6, weighs more heavily than the actual value of 4.8. And I'll only actually use 4.8 if the exponents are the same. So if I have times 10 to the negative 6 up here and times 10 to the negative 6 down here, then I'm going to go ahead and use the number. But since they're different magnitudes, negative 6 and negative 9, I'm going to look at those guys first. And so here in this case, the concentration of OH is greater than the concentration of hydrogen. So if you have more hydroxide, is our solution acidic, basic, or neutral? And so if you had said basic, then you're absolutely correct. Now, what's another way to determine, what's another way to conclude that our solution is basic? Right. And so if we look at the pH, notice that the pH is greater than 7. And so based on what I had mentioned in the previous lecture video, if your pH is greater than 7, then the solution is basic. Okay. Last but not least, if we look at the pOH is less than 7. 5.32 is less than 7. And if we're looking on the pOH scale, remember anything that's less than 7 on a pOH scale is describing that the solution is also basic. If we're using a pH scale, anything that's greater than 7 is basic. And so try to keep the pH scales and the pOH scales correctly aligned in your mind, just because they're opposites of each other. And so it's very easy for you guys to confuse one or the other. Now, if you guys are comfortable with just using the pH scale, then you don't necessarily need to use the pOH scale, because you're going to come up with the same answer, right? It's basic in all three derivations. Okay. One last thing, I don't think I've mentioned this in the previous lecture. Let's go ahead and talk about the pH or the pOH at 7. Let me add some more significant figures here. And so once again, if you're given a pH or pOH, it's the last 2 digits that are significant. The first digit, so anything before the decimal is insignificant, because that number is coming from the exponent in your scientific notation. Okay. And so, and once again, just to kind of show you that a little bit more, if the concentration of H plus is 1.00 times 10 to the negative 7, notice how this 7 is brought forward, okay, as a whole number in your pH or pOH. Oops, I think I pointed to the wrong substance. Same idea though. Okay. And so since that 7 is coming from the exponent, and since the exponent is not significant in terms, it's not a significant digit. Therefore, this 7 is not a significant digit as well. Okay, so that's why it's always important for us to make sure that we have some numbers after the decimal, just so we have a significant digit in our concentration. All right, so anyways, if you guys calculate the concentration of pH, if you guys calculate the concentration of H or hydrogen ion when your pH is 7, you are going to get 1.0 times 10 to the negative 7. And if you guys calculate the concentration of OH when the pOH is 7, that's also going to give you 1.0 times 10 to the negative 7. And you guys can go ahead and perform those calculations on your own just by using the equations that I presented to you earlier on at the very beginning of this lecture video. And so I want you guys to notice that when the pH is 7 and the pOH is 7, the concentration of hydrogen ion and hydroxide ion are equal to each other. And so since they're equal to each other in a chemical reaction, H plus and OH minus together produces water. So in other words, if we have equal parts of hydrogen to equal parts of hydroxide ion, neither chemical species is dominating, and both of them are going to equally neutralize each other to produce water. And so this is the reason why we say that when the pH is equal to 7, the solution is neutral. Okay. Why? Because we've neutralized all of the acids, we've neutralized all of the bases present in the solution, and they're going to form water. And the same thing can be said with pOH. Okay. So if the pOH is, if the pOH is equal to 7.00, then the solution is also neutral. All right. So for you to say if a solution is neutral, both concentrations of hydrogen ion and hydroxide ion must be equal to each other. And if it's not equal to each other, if one is slightly greater than the other, then overall the pH is going to be acidic or basic, depending which chemical species dominates. All right, so that's pretty much it for this video lecture. We went over some calculations for pH, pOH, concentration of OH, and concentration of H+. Definitely keep in mind your significant figures for this specific topic. So one quick trick is to just put in the pH or pOH, and then put in dP for pH or pOH, and then for concentration put in SF or significant figures. And you guys are just going to fill in that number to serve as a reminder of how many sig figs and how many decimal places you need to report. All right, guys, that's it for this video lecture. I'll see you next time. Bye.